So in this video, we're going to do some review problems for an exam in statistics or Math 1025 class. We're looking at review A for exam 1. I'm just going to go run through these. So number 1, we have all cities in the United States is an example of either a sample or a population. To a certain degree, this is a question of how you interpret this. But what I'm going to look at is this keyword sort of all here. So instead of like taking 10% of all the cities in the US or 20 cities from each state in the US or whatever, the idea is we're taking all cities in the US. So I would think that this is B, a population. I suppose you could make an argument that all cities in the United States is a sample of all cities in the world or all cities in North America or something like that. But here I generally think probably we're looking at just cities in the United States for whatever we're looking at. Number 2, we're doing a survey of 1,000 residents of St. Paul. Is an example of so St. Paul has a population that's well over 1,000 residents, and so this is only part of the whole. So because we're only looking at part of the whole, this would be a sample and not the population. Okay, number 3, it says a survey of 5,000 US adults found that 23% of the adults had brown hair. In this scenario, 23% is example of A. So the question here is really if that sort of number, the 23%, came from a sample, then it's a statistic. Note, sample and statistic both start with S. So if the number came from a population, then we're dealing with a parameter. And since we have 5,000 US adults, and presumably we're talking about trying to make a conclusion about all US adults, 5,000 is certainly much less than the total number of adults in the US, so this should be from a sample. And that means that that 23% is a statistic. Number 4. An administrator at Century College determines that the average number of credits taken by a student at Century in fall 2013 is 6.73. In this scenario, 6.73 is an example of A. Well, it really depends on how this was calculated. So did we take all of the students at the college or just some of the students at the college? Now, because we have an administrator, presumably they could go and look at all the data and actually find all of the students at the college. And I'd assume that's what they're going to do here. So I'm going to assume that we're talking about all the students at the college, which is the population. So the 6.73 then would be a parameter because it came from a population. Next one, more data questions here. Hair color is an example of qualitative or quantitative data. So when we have hair color, there's really no number that you could attach to that, or at least in some sort of normal way here. We talk about hair color, we're going to talk about red, brown, black, white, gray, blonde, what have you. And so that's really not sort of as categorical. It's not really a number type thing. So this would be qualitative data. Okay. 6, when we do weight in pounds, well, when we say weight in pounds, that's going to be a number of pounds. There's some sort of number attached to sort of our weight, and that number has some sort of like actual numerical data or numerical value, so this would be quantitative data. Okay, we're going to do some sampling techniques now. So you try to determine the average number of cars that travel across a bridge on Mondays between 7 and 8 a.m. To do this, you count the number of cars that travel across the bridge every 6th Monday for a year. So here what we're doing is we're taking all of the Mondays throughout the year. So there's going to be presumably something like 52 Mondays. And so we take maybe the 1st Monday, and then the 7th Monday, and then the 13th Monday, and the 19th Monday, and so on. Here, what we're doing, so we're jumping by 6 each time. So this is really a setup for systematic sampling. So what we're doing is sort of taking every 6th or every nth member of a population, and we get our sample that way. There's still a lot to be determined here, like how you count those number of cars. Maybe you can actually count them all. Who knows? It depends on how busy the bridge is. Let's see. So in 8, an instructor wants to determine the average number of hours spent studying for an exam by students in a particular section with 30 students. So the instructor uses a computer program to randomly select 5 students as a sample, and then presumably ask those students how much they studied for, or I don't know, videotape them for a day, which seemed kind of strange, but somehow we're getting the number of hours spent studying by those particular 5 students. And when you use a computer program to randomly select The idea here is this is probably a simple random sample. So we're doing simple random sampling. So we could really go and like label the students from 1 to 30 and go pick 5 random numbers from 1 to 30, and that would give us a simple random sample. It's very feasible here, so we're going to assume that's what we're doing. Okay, let's up a little bit more. Down a little more. There we go. Okay, so an instructor, for number 9, an instructor wants to determine the average numbers spent studying for an exam by students in a particular section with 30 students. Same setup as the last problem. So what we do is this instructor selects a sample of 3 male students and a sample of 3 female students. The combined 6 students are used as a sample. So what we did is we took all of our students here, and then we split this into 2 groups. So we had sort of our male students here, and then we had our female students here, and then we took a sample from each of these 2 groups. So we split into groups, and then we took a sample from each of the groups. So what we did here is we took this color, we took maybe this person, and this person, and this person, and then amongst the female students, we took this person, and this person. So we split sort of our whole population into some number of groups, in this case 2, and then we took a sample from each group. The idea here being that maybe male and female students study for a different number of hours, perhaps. We're trying to guard ourselves against that. So this one, when you split into groups and then take a sample from each group, that is going to be stratified sampling. So really we'd say we'd split into strata or 2 stratum, or each is a stratum, split into 2, and then we took some number of members of each of the stratum. Okay, next one. Century College wants to determine, whoops, where'd we go? Century College wants to determine the average number of hours spent studying for a statistics exam. The college decides to sample all of the students in 3 sections. Sampling technique used is, well, so what we're going to do here is you've got sort of a whole bunch of sections of statistics. I think there's 9 this semester, it turns out. So you split this into a bunch of groups here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then what you're going to do, apparently, is we're going to select 3 of the sections. So let's say we select this section, we take all of the students in here, maybe we take all the students in this section, and maybe we take all the students in this section. So we pick 3 sections and we take all the students from all 3. So this is cluster sampling here. The idea here is we split into groups and we took all of some of the groups. Note, if this was stratified, we would take some students from each group. Now, probably you're going to get a better estimate if you did stratified sampling and you took like 5 students from each section, or however many you'd want to take here. The advantage of cluster sampling is that when I take all of the students in each of these sections, I can just go to one section and then go and ask everyone in that section how many hours they studied. Here, and I don't have to, sort of easier logistically, I don't have to go to a bunch of different sections. Again, the problem is maybe this section the students are studying an awful lot because the exam is particularly hard, or the students in that section are in there because of some other class combination they have, and they therefore study more or less than other students. And there might be some reason why the students are in that section. So this would be cluster sampling, though. Okay, now into more data questions. Whoops. So consider the following data. We've got a bunch of numbers here. We want to fill in the frequency distribution chart. So really, all we're going to do is count how many numbers we have between 31 and 34. So 1, 2, 3, there's 4 numbers between 31 and 34. Between 35 and 38, we have the 36, 37, 38, 38, 38, 1, 2, 3, 4, 5. Between 39 and 42, we get 1, 2, 3, 4. Up to 46, 1, 2, 3, 4, 5. 47 to 50, there's 2. No, normally these wouldn't necessarily be sorted. That just really simplifies the counting process, so you don't have to hunt around and find things. So hopefully that part's pretty straightforward. We're just counting how many numbers are in each range, how many elements of our data set are in each range. Now the relative frequency here, that's sort of the percentage of the data set that's in that range, of the whole data set. Now one thing that would have been nice to do here is maybe add these up, 4, 9, 13, 18, 20, and then make sure we got all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2 is 20. So there's a total of 20, so we didn't like miss one or something. Now, because we have 20, our relative frequency here is going to be 4 out of 20. Note that's 1/5 or 0.2. The second category, we had 5 out of the 20. That works out to be a fourth or 0.25. Third category, we again had 4 out of 20. That's 1/5 or 0.2. We then get a 5 out of 20 again, which is 1/4 or 0.25. And then we get a 2 out of 20, which is 1/10 or 0.1. So the relative frequency is just the frequency divided by the total number of elements in the data set. Cumulative, what that means is we're going to sort of add as we go down. So we're going to start with 4. Keep jumping around. Start with 4. And then the next one isn't asking us how many are in this category. It's asking how many are in this category or any of the categories above it. It's really going to be the 5 plus the 4. That's a 9. The next one is really the 4 plus the 5 plus the 4. Now, there's a couple ways to get this. Probably the more inefficient one is 4 plus 5 is 9, plus 4 is 13. Alternatively, you could have said, well, we had 9 above here, and then we just added 4 more. So 9 plus the 4 gives you the 13. Next category, I'm going to do the same thing. I had 13 from these 3, plus 5 more is 18. And then 18 plus 2, that gives me 20 in that class. Note, 20 is the total number of elements in our data set. It's a nice check that that works out. Okay, next question. Let's see, we've got the sizes of televisions available at walmart.com are described in the following histogram. About how many televisions are there that cost $500 or less. So we're just trying to basically read the histogram, read the chart here. What I'm going to do here is I'm going to say $500 or less. I'm really in these first two categories. This first one, now I can't tell exactly how many that is. Note it says about, so there's some sort of estimation. I'm going to say maybe that's 3/5 of the way up. So maybe that's 30. Sometimes these charts will actually have a number on top of each of these vertical bars, which will tell you exactly how many there are. This one, maybe that's 4/5 of the way up. Maybe that's 140. So it's nice to write those so I can say the total number is 30 plus 140. That's 170. So in a question like this, if you're anything at all close, that's fine. Again, it's a good idea to write the estimates you use so that we can say, oh, you add those, and we can check each of the estimates. Are they sort of reasonable? Okay. Next one, we have a data set. We have to find the mode, the median, the mean, and some other things here, variance, standard deviation for sample and population. So first thing, mode, that's the most common number. So in this case, we have a, let's see, we have a 8, 3, 4, 7, 9, 2. There's 2 3s. So 3 shows up twice. No other number is repeated, so the mode is 3. Median, sometimes it's helpful to reorder these. It's 2, 3, 3. Maybe I'll cross these out as I go by. 4, 7, 8, 9. The median is the middle number. So there's 1, 2, 3, 4, 5, 6, 7 elements in our set. So this 4 is going to be the median because there's 3 less than that, 3 less than 4, and 3 bigger than 4. Median is 4. Now the mean, this is sort of the average, the way that people normally think of this. And so what you do is you do 2 plus 3 plus 3 plus 4 plus 7 plus 8 plus 9, and we divide by 7. Whoops. What you get, let's see, 2, 5, 8, 12, 19, 26, 35 divided by 7. That's actually going to work out to be 5. So your mean is 5, mode is 3, median is 4. Okay, now we've got our variance, standard deviation questions. So the first pair, if this is a sample, what is a sample variance? What is a sample standard deviation? I'm going to run through this calculation down below. You can see the elements of the data set in this sum here, 2, 3, 3, 4, 7, 8, 9. And when we do our variance here, what we do, let's just write those down. 2, 3, well, let's do it this way. X here is 2, 3, 3, 4, 7, 8, 9. We need to do x minus mu, or I suppose x minus x bar, if this is a sample here. Maybe do that. or you could think of it as x minus x bar. Either one of these is just x minus the mean, so minus 5. So this is minus 3. 2 minus 5 is minus 3. 3 minus 5 is negative 2. 3 minus 5 is negative 2. 4 minus 1 is negative 5. 7 minus 1 is 2. 8 minus 5 is 3. 9 minus 5 is 4. And then we need to do x minus mu, and we square. Or x minus x bar squared if it's a sample, which is the case here. So negative 3 squared. The negative really doesn't factor in. It's 3 squared is 9. 4, 4, 1, 4, 9, 16. And then what the variance is, the sample variance, what we're going to do is we're going to add up x minus, okay, it should be x bar for a sample variance squared, which is really just the same numbers. We add up these 7 numbers here, and we divide by, there's 7 numbers, but for some kind of strange technical reason that we're not going to get into, instead of dividing by 7, you divide by 7 minus 1, if this came from a sample. So what I get here, this is 9 plus 4 plus 4 plus 1 plus, whoops, I missed a 4. 4 plus 9 plus 16, and then I divide by 6. Let's see, that's 9, 13, 17, 18, 22, 31, 47 over 6. Might be a good idea to write that as a decimal here. Let's just do 47 divided by 6. So it have to be 7.833. So this turns out to be something like, maybe approximately, we should write 7.83. So that's our variance here. I'm just going to write 7.83. So that's our sample variance. Our sample standard deviation, note sample variance, that's sigma squared. Sample standard deviation, oh, sorry, it's not sigma squared. It's a sample, it's s squared. Population variance is sigma squared. So the sample standard deviation, all we need to do is take the square root of both sides up here. So this is square root of, well, I guess 47/6 will give us a more accurate answer. Actually, this is actually straight up equal to, if we don't approximate. And so we could do second square root, 47 divided by 6. That's 2.7988 maybe. Here's where we work through. So it's something like 2.7988. Okay, now, if the data set represents a population, the only thing that changes here for a population is I take really these same numbers. So that's really, whoops, I want a different color here. Tell the population calculation. And it's sigma squared is the sum of x minus mu squared. Now, mu and x bar are the same numerical value, so it doesn't matter which one you use. And now, instead of dividing by this 7 minus 1, I just divide by 7. So this is going to be the same 47 divided by 7. Now, instead of 6, now we'll get a slightly smaller answer because we're dividing by something that's slightly bigger. We get 6.71, no, slightly bigger than 7.83. So something like 6.71. So this is now sigma squared is approximately 6.71. And then if the data set represents a population, what is the population standard deviation? So this answer is sigma. Well, that's just the square root of sigma squared, which is the square root of 47/7. Again, let me rewrite this so it's a little bit cleaner. This is actually straight up equals square root of 47/7. And what we get when we calculate that is square root 47, whoops, divided by 7, 2.5912 if I go to the same number of decimal places. It's the last one. So this is like 2.5912. Oh, so we get, whoops, get this answer, get this answer. I'll circle these in blue as well here. So you can calculate these directly. Now you can also sort of make the calculator do the work for you. And so what you can do is you can go to your calculator. I'm going to change the view here. Let's see, hide our key press history, a bit smaller. So we can enter in these numbers here. So what I'm going to do, I'm going to go to Stat. I'm going to go to Edit. I'm going to enter these numbers into L1. It doesn't really matter what the order is. I'm going to go with the original order. 8, 3, 4, whoops, no, I didn't get the 3 there. 3, I didn't hit enter. 4, 7, 9, 2, and 3. So that's the 7th number. That's good. I'm going to quit out of this. So I just want to enter these numbers into L1 or whichever list you want. And then what I'm going to do is I'm going to go to Stat. I'm going to go to Calc. I'm going to pull out one variable stats. Now some of you will have calculators where you get kind of a menu where you have to pick the particular list, the L1. If you get a frequency, like an FREQ looking thing, generally I think you want that to be 1 here. Here we don't want to do that. We could do comma and then put the frequency list, but we don't need to do that. So one variable stats gives us a whole bunch of information. A couple things. This X bar, that's the mean, 5.14. Oh wait, we got a mean of 5. So that tells me either I miscalculated this mean or I misentered some of the data. So let's go back and look at our list here. Edit. Let's see, we have 8, 3, 4, 7, 9. 3, 4, 7, 9, 2, 3. And this is kind of a mess here because presumably 8, 11, 15, 22, 34, 30, wait, 8, 11, 15, 22, 31, 33, 36 here. So the mean, this 35, I apparently misadded this here. So this, let's do a bright green here. That doesn't show very well. Let's do it in green. This 35 should be a 36. And now, unfortunately, that's going to throw off all of our numbers here. So this 5, and we go through, it should be 36 divided by 7. So we're going to recalculate these. Sorry about that. So this is something like, whoops, 5.14 here. Or maybe that's approximately equal. That's going to throw off these numbers as well. Note, we've got the right data values, but this mu that we're subtracting is now the 5.14. So what I would want to do here, let's see, 5.14. When I do, I'm going to have to delete sort of all of these numbers. Go away, delete them, missed that one here. So when I do the x minus mu, it's 2 minus 5.14. So I can get rid of, let's see, that's going to be negative 3.14. It's going to be negative 2.14. Is that right? 2 minus 5.14. Let's see, so it's the same thing. Yeah, that should work out. Okay, and then 5.14 plus 3, or sorry, 5.13 minus 5.14, another negative 2.14. Can give me negative 1.14. Now 7 minus 5.14 is going to be 1.86. 8 minus 5.14 is 2.86. 9 minus 5.14 is 3.86. And then I have to square these numbers, which I can't really do in my head. So I'm going to get 3.14 squared. Oops, I didn't get everything there. 3.14 squared. Note I'm getting some error because that 0.14 is rounded here. I'm just going to live with that here. What we get is a 9.86 for that one. And then when I do 2.14 squared, you get a 4.58. I'll get another 4.58. And then it's back over. 1.14 squared. Didn't get that right. 1.14. Still not getting it. 1.4 squared. It's 1.30. And I got 1.86 squared. Note when I did these earlier squares, I didn't need the negative because when you square a negative, you get a positive anyway. So I get 3.46. You have 2.86 squared equals 8.18. And then we have 3.86 squared, and you get 14.90. So then I have to add up all these numbers, and so that 47, instead of 47, I get the sum of these things. which, let's see, that first one was 9.86, so I get 9.86 plus 4.58 plus 1.3, didn't get the 1. Do second, insert a 1. And if I hit second and right arrow, it'll take me all the way to the end. Plus 3.46 plus 8.18 plus 14.9. So I get 42.28 here. And that means that I'm going to divide that by 6. Gives me a 7.05 for my sample variance. So this 7.83 is 7.05. And then this is going to be square root 7.05 for the sample standard deviation. And now I could do just second square root, second, the negative t gives me the answer, so that's 7.04. Gives me 2.65. I'll put this here, just the 2 digits. And then our population variance, we're going to copy the, what is this, 42.28. Clean that up because I'm misreading it already myself. So this is 42 point, oh, I forgot already, 28. So this is not 47, it's again 42.28. It could be 42.28, and then divide by 7, 6.04. Actually works out to be, well, it works out to be exactly 42.28 divided by 7, but that 42.28 was rounded here. So this again is 6.04. And then we take the square root of 6.04 here. And what we get is 2.46. So our numbers changed to some degree. They all got a little bit smaller, it looks like, here. Okay, so we got those numbers. Now let's go back and check with the calculator. Whoa, that's a mess. Do it this way. Okay, so we go to stat. Oops, we already entered our numbers in, so I don't actually need to do that. Well, no, I do. Stat, calc, one variable stats. Go back to L1. Second, the 1 gives me the L1. And what I get now in one variable stats. So now I get the 5.14. So it's nice that I checked that. Now we got to look at this. So SX, that's our sample standard deviation. That's the 2.79. So we're getting here 2.65. It's a little bit off, but there's some rounding. Perhaps that's okay. Population standard deviation is 2.58. We're getting 2.46. Again, a little bit off. There's some rounding. It's okay. What I could do is square the 2.79 and hope I get something like 7.05. I could square the 2.58 and hope I get something like the 6.04. We'll do that in a bit here. As I go down, note there's a couple other things, like the median is 4. It doesn't give you the mode. So it gives you the median as well. And then this is your 5-number summary. Here your minimum, your Q1, first quartile split off, median, third quartile split off, and then the max. Okay, so now let's talk about how to get the actual sigma x value and sx value out of the calculator. So you could type this all out, but what's easier to do, so we're sort of on the home screen now, is I can go to variables, go to stat, option 5, so I just hit the 5, and then I have sx right there, and I could do sx squared. So sx is the sample standard deviation, so give me the sample variance, and now I'm a little bit concerned about this here, because you'll note here that this sample variance is closer to the original thing we have. So instead of 7.05, it's 7.83. Makes me wonder if I miscalculated something here. So I'm going to go back. Maybe I'm going to recalculate. How about this 42.28 thing? Actually, a nice way to do that is if you go to stat and edit, you can go over to L2 here. And what you can do now is you can make L2 be L1 minus the 5.14. And then what that's going to do is take 8 minus 5.14, 2.86. 3 minus 1.14, or sorry, 5.14, negative 2.14. Now we've got these in a little bit different order. Where we get the 2.86, we get a negative 2.14, we get a negative 1.14, 1.86, 3.86, and then a negative 3.14 and a negative 2.14. So those all look good. Now what I can do is I can go over here, could have done this in one shot, but I'm going to go over here and make L3 second, make this L2 squared. So it's going to take each entry of L2 and square this. And so that tells me I should get an 8.18, essentially, 4.58, 1.30, 3.46, 14.9, 9.86, 4.58, and 2 of those. So all these numbers in this table here, those actually look good. There's some here. Let's go through and calculate that again. There's a way where if you do stat, no, I think it's actually list, second, and then you hit list. You go to ops, or maybe it's math. Yep, math sum. So we can do a sum of L3. That's really what we want. Tells me I should get 46.86. So this 42.28 is apparently wrong here. So let's go through and recalculate that. 9.86 plus 4.58 plus 4.58 plus 1.3 plus 3.46 plus 8.18 plus 14.9, and that's going to give you a number like 46.86. So I've already messed this up twice here, so this should be 46.86. Here as we go there. Now, a couple points here. I don't really want to go through this calculation again here. Well, no, let's just do it. So 46.86, I'm going to divide by 6. That's going to give me 7.81 here. So that's the 7.81. And then I can take a square root of that. I get his second answer. Square root, I get like 2.79 here. And then for the population variance and the population standard deviation, I take the 46.86, so I get rid of this, 46.86, and I divide by 7. 46.86, and you divide by 7, you get like 6.69. Note, much closer to the original values we had. Let's see, it's the population variance, 6.69. And then our population standard deviation, the square root of that, which gives us like a 2.59. 59, and that's a mess. Here's what that is. So the population standard deviation is 2.59. Okay, a couple things here that sort of we can recap here. So you'll note I made some mistakes here. One thing that will help you in terms of partial credit is sort of showing work here, and it's clear that, oh, you had the right numbers here and you added them up, you didn't get this here. Actually, if you think about what happened, one thing I could think about is let's take a difference of 46.86. 46.86 minus, minus the 42.28. What I wonder is if I didn't just leave off one of the data values, I get 4.58. So my guess here is that what happened when I did the 42.28 is I did a 4.58 once and then didn't do the second one here. So that's probably the error I made, but you know, I add these up. It's a little bit of a bad error in the sense that it's not clear, like perhaps you didn't understand that you had to add up both of these, I guess. But still, you kind of can see what happened here. You show enough work, or you might be like figure it out. So you've got that point here where showing your work is good for partial credit. If you just gave an answer like 7.05, it's really hard to get much partial credit because I don't know what happens. So if you did all these calculations on your calculator or on a scratch paper that you didn't turn in here, it's very difficult to figure that out. The other thing, and you're fine on the test, just going through and using the one variable stats here, I know that makes some students uncomfortable here. Somehow you feel like you want to do some work, but the point here is a lot of times you're going to make fewer errors when you use the technology to sort of streamline things with like 7 numbers here. Like I made those errors actually unintentionally, but sort of a teaching moment, I guess, here that you can make errors. And how to reduce them is the technology does the sort of tedious stuff for you and is much more consistent, at least than I am. Okay. Next one. Consider the following data set. I'm going to draw a stem and leaf plot for this data set. So our stem and leaf plot, basically what I'm going to do is I'm going to just write the tens digits down here, down first. So we have 1, so we're in the tens up to the 50s. So I'm going to write our tens, 20s, 30s, 40s, 50s here. And then what I'm going to do is I'm going to find my 15, I'm going to put a 5 there. So tens digit, ones digit. I'll get rid of the 15. 59, I have a 5 and a 9. 24, 2 and 4. 34 is 30 and a 4. And now 33, I'm going to do 30 and then just put the 3 there. Another 34, I'm going to put another 4 there. 25, I'm going to put a 5 there. 41, I'm going to put a 1 there. 52, I'm going to put a 2 there. 31, I've got a 1 here. 22, I've got a 2 here. 48, I'm going to put an 8 there. 38, I'm going to put an 8 there. 18, I'm going to put a 1 and then an 8. 42, it's a 4 and a 2. 50 is a 5 and a 0. And I'm fine if you leave this like that. What you can see is that sort of the most numbers are in the 30s here. What some people will do is rewrite this 1, 2, 3, 4, 5, and then sort of order each leaf here, or order the leaves. So this is our stem, the 1, 2, 3, 4, 5, and these are our leaves. So what we might do is do instead of 4, 5, 2, do 2, 4, 5. Put those in increasing order. This we could do 1, 3, 4, 4, 8. It's nice if you want to keep these numbers in a column because the point is you want to be able to see how many there are here. If you kind of squish these ones together, it's not clear visually right away how many there are in each row. Next one, 1, 2, and an 8. And then I get a 0, 2, and a 9. So either one of these, for me, would be acceptable answers. Here, sometimes the sorted one's a little bit nicer to see things from, but this is just fine. Okay, now these two questions, I'll admit, are from an old exam format. These are things that we'll really do later on. You may understand these. I'll go through them right now because they're here. So 15, I'm going to assume the weight and heart rate of an animal have a negative linear correlation. So what that means, if I graphed here weight and heart rate, if I did a line between weight here, so this is weight here, and I have heart rate here, that line is going to have a negative slope. So I'm going to sort of best fit this line here. That's pretty uniform. There's a few weird ones somewhere, but there's some line that has a negative slope. What that really means is the larger the weight, the lower the heart rate. So if weight goes up, heart rate goes down. Also, if heart rate goes up, weight goes down. So what we would expect here, okay, squirrel has a greater heart rate than an armadillo. So I was going to be concerned that people maybe don't know what armadillo is here. So it says if a squirrel weighs 2 pounds and an armadillo weighs 12 pounds. So whatever an armadillo is, it's heavier than a squirrel here. So armadillo has a higher weight, which means it should have, because of the negative correlation, the armadillo should have a larger weight, should be a smaller heartbeat. So the squirrel should have a greater heart rate than the armadillo. So armadillo has a smaller heart rate, means the squirrel has a larger heart rate. 16, assume the wattage of a light bulb and the number of lumens the bulb produces are positively linearly correlated. So when this is a positive correlation, what if I do is, how about watts, wattage, and then you have the number of lumens, say on the y-axis, and I put a bunch of points here. My best fit line is going to have a positive slope. It means watts goes up, lumens goes up, watts goes down, lumens goes down. So I'd expect here a 60 watt light bulb should produce more lumens than a 45 watt light bulb on average. So larger watts equals more lumens. You just check through. 45 watt light bulb produces more lumens. Now it should be less lumens than a 60 watt light bulb. Okay, a couple more. Consider the following two data sets. So my instruction here apparently is not any good. I'm just going to say consider the following data set. That's really all I need. We can look at this and we say, what is the median? So what's going on here is we have 15, you can tell because it's between 14 and 16. We have 15 sixes and we have 10 ones. Now you could go through and calculate directly. The point of this question is to be able to calculate this without like putting in a list with 10 ones and 15 sixes. So the median here, well, if I think about this, if I order these out, I'm going to get 10 ones, I could have 10 sixes, and then the middle 5 numbers will all be sixes. So that middle number is going to be a 6. The mean, well, if you look at this, I have 10 ones, that's 10 times 1, plus 15 sixes, that's going to be 15 times 6, and I have 10 plus 15, 25 total numbers. So it's going to be 10 plus 90 over 25 is 100 over 25. That means the mean is 4. So our mean is right here at 4. The mode is the most common number. That's the 6. You note the median and the mode are common. And then we've got this kind of peculiar question here of, is the population standard deviation larger or smaller than 4? So this standard deviation, what it's supposed to be is some sort of average of how far the data elements are from the mean on average, and some kind of funny average. So if you have a 1 here, this distance from 4 to 1, these are distance 3 away. Maybe it's 1 minus 4 is negative 3, but when we did that variance calculation, it's squared, so it's really the absolute value, the distance that matters. And once you do the standard deviation, you're like taking a square root, which kind of gives you an average. From 4 to 6, that distance is 2. So we're going to say it's the furthest any element of the set is from the mean is 3. That's going to mean that our standard deviation can be at most 3. So I'm going to expect it to be somewhere between 2 and 3, some kind of funny average of 2 and 3. And that means that the standard deviation, larger or smaller than 4, must be smaller than 4. Here. So it's somewhere between 2 and 3. Now you can actually use your calculator to go through and calculate these things. So what you could do is go to Stat, Edit. Now if I want to clear these lists, I go up to L3, hit Clear, and Enter. Go up to here, L2, hit Clear, Enter. Go up to L1, hit Clear, and Enter. What I can do is say, okay, I've got 1s, I've got 6s, and I mean, I could enter 1 10 times, enter 6 15 times, but what's easier to do is go over here, and then you're going to have your frequency list. This is 10, and then 15. So I'm saying I have 10 1s and 15 6s. Now what I can do, quit out of this, I can go to Stat, Calc, one variable stats. So the numbers are L1, but their frequencies, I'm going to do comma L2. So I hit the comma key above the 7, and they do L2, and now I hit Enter here. If you have the sort of menu thing, you put the, I think it should be an FREQ menu, and you put L2 there. So what we get is X bar, that's the mean, that's 4. Note it's nice to check, like N is 25, 10 plus 15 is 25. That's a nice thing to check that you didn't swap L1 and L2 from what you wanted. Let's see, what else do we want? Median, we can probably pull off if we go down here. Median is 6. And then the population standard deviation, that's this sigma x, that's 2.44, which is in fact smaller than 4. So we set up here that population standard deviation should be some kind of average of 2 and 3. And it's a little bit closer to 2. It's some kind of funny-ish average, but somewhere between 2 and 3, which we can see we got. If there was a sample, you'd have a 2.5. Actually, it doesn't even say, well, wait, did the question say population standard deviation? Could have been sample standard deviation, doesn't matter. Okay, same vein here. We've got 2 data sets, chart B and chart C. Which data set has the higher standard deviation? So if we look at these, really, our standard deviation should be sort of an average-ish distance from the mean. So if I was going to guess the means here, probably something like 4-ish for B, probably, let's see, maybe somewhere like 4-ish for C as well here. And if you look at this, B, sort of most of the data is really 4. So it's really a lot closer to 4 on average. The one, like the 1 and the 6, there's not as many of those compared to the 4s. For C, things are a little bit more uniform. They're a little more spread out. And that means when we average these, what we're going to get here is these large distances. In this case, 2 and 3 are the large distances, large in comparison to 0 from 4 or 1 from 4 if it's 3 or 5. Probably not actually 4. It's probably like 4.1 or 3.98 or something like that. But in any case, the 6 and 1 are going to be the furthest distances away here. And really, proportionally, C has more 6s and more 1s. So a higher percentage here of the data for chart C is in the 6 and 1 category. The farther away points should mean that C generally is going to have a larger standard deviation. So here, this is going to be C here, should have the larger standard deviation. Okay, now on to probability. So 19A. Find the probability the sum of dice is 9. We're rolling 2 dice. So what we get is there's 36 possible combinations here. And we figure basically our numerator then is going to be how many of them equal 9. So you could make a chart and count those. What I could do is I'm going to tend to think about, well, the smallest a number could be in it equal 9, could be and be a sum up to 9 of 2 dice is 3 plus 6. So if I have the 6 plus the 3 gives me 9. I'm just going to step the 3 up 1, means I have to step 1 down with the 6. 4 plus 5, and then I get 5 plus 4, and then I get 6 plus 3. So I could get a 3 and a 6, a 4 and a 5, a 5 and a 4, a 6 and a 3. So I have 1, 2, 3, 4 out of 6. Should probably simplify that to 1/9. Next one, find the probability the sum of the dice is 5, or at least one of the dice is a 3. So what we could do here, sum of the dice is a 5. Well, that gets a little bit messy here. Maybe we're going to, well, it could be 1 and 4, 2 and 3, let's just write it out, 3 and 2, 4 and 1, and then at least one of the dice is a 3. That was one of those sort of cross situations here, where we had 3s, like this was like 3, 1, and then 3, 2, and then 3, 3, 3, 4, a 3 and a 5, a 3 and a 6, and then this one would be, let's see, 1 and 3, 2 and 3, 4 and 3, 5 and 3, 6 and 3. So this is the, at least one of the dice is a 3 over here. If you count these, you think they're 6 and 6, that'd be 12, except we counted the 3 and 3 twice. So to subtract that off, so it's really 6 and then 5 new ones, so there's 11. Now, the general strategy here, we have 36 total, is you would take these 4 plus the 11, so the 4 that gives us a sum of 5, plus the 11, where we have at least one of the dice being a 3, except then we have to subtract off the part where we have the sum of 5 and at least one of the dice is a 3. So if you look at this, this 2, 3 pops up here. And this 3, 2 pops up here. So what we need to do is we need to subtract those two off. And the reason we're subtracting them is we're counting them in both of these sets here. So we only want to count them once. We counted them twice. So to get rid of them once. That means we've counted them overall once. And so what you get here is 4 plus 11 is 15, minus 2. You get 13 out of 36 here as your probability. So that's one approach. The other thing you can do is fill in this whole chart, and you get these 11. Note you would also get the, let's do purple, how about? This would be the 1 and 4. This would be the 4 and 1. And so you sort of extend what you're counting here. And so you can just count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total that work. I mean, you could fill in the whole chart and do that if you want. Maybe another way to do it, but sometimes I worry that I'm missing one or something. Okay. Next one, we're dealing with cards here. So you draw 2 cards from a standard. It's going to be a 52 card deck. Find the probability that both cards are spades. So a couple ways to do this. One is I'm going to worry about the probability the first card is a spade. So that's 13 spades out of 52 cards. Then I'm going to assume that the first card was a spade. Then what's the probability the next card is a spade? So if you think about that, there's 51 cards left. We already pulled out 1 spade, so there's 12 spades left. This calculation is then 1/4 times 12 and 51 actually simplifies to 4 17ths. So 12 and 51 both have a factor of 3. 3 times 4 is 12. 3 times 17 is 51. The 4's cancel, and we get a probability of 1/17. So that's one way to do this. Another way is you could think about, well, if I'm going to draw 2 cards out of the deck, I have a 52 choose 2 number of ways I can do that. Now if the 2 cards are spades, that would be 13 choose 2. And so I can calculate here on my calculator. I can do 13 math probability NCR2, close parenthesis, and then divide by 52 math probability NCR2. And that should give me the same probability. So what I'm getting here is, what's an approximation, 0.0588. Now, is that the same thing as 1/17? You could do 1 divided by 17. You could also hit math, and the first option and sort of the first menu is convert to a fraction. So it converts that to a fraction. It is actually 1/17. So either one of these methods is okay. Another option is you could, this here is paying not attention to order. So it's like I get 2 cards at once and just sort of pick them up at the same time, and I don't really care which one was first, which one was second. You could also run the same kind of calculation, paying attention to the first card and the second card. And so what that would be is you'd have 13, I'm just going to write it in the calculator notation, but 13 NPR2 over the 52 NPR2. So I do the permutations here. Note these numbers are going to be different, but if I do 13, probably I do NPR2, and then I divide by 52 math probability NPR2. What I get the same thing. So let's do an approximately equal, 0.0588. You can see it's the exact same decimal. It will convert to 1/17 as well. So you can do really any of these 3 ways. To me, this blue method feels a lot more natural than the red method, but that's probably more just because of what I've been exposed to than any sort of inherently simpler thing in the sort of mathematics. The green method works pretty well here. One thing we don't like about this method is you can imagine a situation where I've got a deck of, I don't know, there's a deck with 500 cards and there's 125 spades, and I'm going to figure out the probability that I get 12 cards and they're all spades. I have to do 12 separate multiplications here, whereas this method would look exactly pretty much the same. It'd just be 125 choose 12 over 500 choose 12. So it sort of generalizes much better, the blue and the red. Okay, again, we're pulling 2 cards. Find probably the first card is a spade and the second card is a heart here. So like the green method, what this would be, first card is a spade. That's 13 out of 52. And now, once I pull out that spade, there's 51 cards left, but how many hearts are there? There's still 13, because we already pulled out 1 spade. So we don't drop to 12 because it's not the same suit. Now this, I'm just going to approximate here. I could try and convert that to a decimal, or to a fraction. Simplified. So 13 out of 52, that's really 1 out of 4 here. 13 divided by 51. I'm going to get 0.637? Yep, 637. There. Now, I can do something similar with this kind of blue method where I'm doing the combinations. And so what I got to think about here is my denominator is still number of ways to choose 2 cards. And I got to think about how many ways can I get a spade as the first card and a heart as the second card. Now, actually, I run into trouble here because I'm specifying an order, and so this blue method doesn't work very well naturally. I want to actually do this permutation method. I'm going to skip the blue, and I'm going to make my denominator 52 NPR2, 52 P2. And then what we have then is 13 choices for the first card and 13 choices for the second card. And you can see you get 13. Could do 13 squared, but I've got times 13 divided by 52 math NPR2, and that should give me hopefully the same decimal, and you see I get the exact same answer. It's an approximate answer, so I like to put the approximately equal to here because it's not exact. So 0.0637 again. So you can do either of these methods. There's kind of a way to do the blue, but I feel like it's a little bit awkward here. Okay, last one. Find the probability that we get one of the cards is a spade and the other card is a heart. So what we're going to do here is you could say one of the cards is a spade, other cards are a heart. Well, we could have two options. You could have heart and then spade, or you could get spade and then heart. So if you heart and then spade, that's 13 out of 52 times 13 out of 51. That, or we're going to add spade and then heart, also 13 out of 52 times 13 out of 51. Same reasoning as up here. Really what we got, if you look at this, is 2 times 13 out of 52 times 13 out of 51. We got twice the probability we had before, which makes sense. We could get a spade and then a heart, or a heart and then a spade. So what I'm going to do is I'm going to take my previous answer. Let's just do it out. 2 times 13 divided by 52 times 13 divided by 51. I was tempted just to hit times 2 to multiply the last answer by 2. Somehow that doesn't show you where this came from. So I get something like 0.127. That 4 would round up to a 5. So 0.1275. I go to 4 digits. Now, because we're not specifying the order these come in, this is sort of more naturally one of these combinations than a permutation. So what I can get in my denominator is 52 choose 2. And then I have 13 possible spades and 13 possible hearts here. I don't have to pay attention to the order. So I go to my calculator. This is 13, let's do the squared this time, divided by 52, math prob, now NCR2. And that should give me the 0.127, which it does. So this is 0.1275 here. It's approximately equal to. Here. So I could do either the green method, either the blue method. So each of these questions, you only need to do one method, but sometimes it's nice to have options here. Another thing that's nice on a test is if you get done 20 minutes early, do it in the other way, or 10 minutes early, or 5 minutes early even. Do the problem both ways and see if they match up. If they don't, it tells you at least one of them is wrong. Then you want to make sure you pick one and say, oh, this is the one I want at the end. Make that very clear, circle it, maybe write an arrow and say use this one or something. If it's not clear, or sort of just cross this out. I generally would discourage erasing this. I see students do that. And the problem then is maybe this was right and you can't tell. Particularly, you might not get any credit for it, but when you get your exam back, it's like clear that was correct. The other thing that happens is sometimes you erase this one, and then you 5 minutes later, you're like, oh no, that's the thing I actually want, but now I've erased it. So if you cross it out, sometimes that's fine. Come up and ask if you're not sure if your answers are sort of clear which one you mean. Okay, last couple questions here. So 21, you need to work 4 days out of a 7-day week. How many different combinations of days could you work? So we've got 7 days, and we need to choose 4 of them. So this is either going to be the 7 choose 4, which is the 7 NCR4, or this is going to be the 7 NPR4. So we're going to do permutations or combinations. And the question is which one is appropriate here. So the main difference is we do the combinations here when really the order doesn't matter. We do the permutations when the order does matter here. And so what I'm going to say is 4 days a week, I would say if you got assigned to work Monday, Tuesday, Wednesday, and Friday, that's really the same thing as working Wednesday, Tuesday, Friday, and Monday, or whatever. So it doesn't really matter what the order is. Let's actually do these in a way that would be coherent here. So these are in the order in a row. Maybe we start on Friday, and then we go to Monday, and then we go to Tuesday, and then we go to Wednesday here. So if you started at Friday and started counting around, maybe those are the days you work. But essentially, you're working the same days. So that tells me the order you list these in really does not matter. And so I don't want the permutations. I want the combinations. And I can calculate that a couple ways. You can do 7 math prob NCR4. That's fine. Now make sure you write down 7 NPR4 on your exam here, just so you have some notion of where that came from. It might help out with partial credit. You get a 35. You also could have calculated this binomial coefficient as 7 factorial over 4 factorial times 7 minus 4 factorial. That's 7 factorial over 4 factorial times 3 factorial. And then what I do is 7 math prob factorial divide by, make sure you put this denominator in parentheses. You get 4 math probability factorial times 3 math probability factorial. That works out to be 35. Note, one mistake I see a fair amount of is if I don't include these parentheses. Whoops, I can delete that. So if you don't put these parentheses, you get a different answer. And so what's going on there, let me write down the 35 here, is that when, purple here, if you do 7 factorial divided by 4 factorial times 3 factorial, order of operations says do the set, well, the factorial is going to take precedence here. We're going to do 7 factorial divided by 4 factorial, and then we're going to multiply that whole thing by 3 factorial. Effectively, what you're doing is moving that 3 factorial to the numerator by doing that. So instead of this, you need to make sure here that you have these parentheses here, or instead of multiplying by that 3 factorial, this I think is a little slicker in terms of what you enter, but it's a little more confusing maybe, is I divide by it. And dividing by it gives me a 1 over 3 factorial, and that gives me the 35. Somehow that's trickier to think about, but maybe easier to actually enter in your calculator once you get used to it. Okay, last one. From a group of 12 people, you are to pick a president, vice president, and treasurer. How many ways are there to make the selection? So here again, we're going to either get 12, choose 3, the 12 in the calculator NCR3, or we're going to get the 12, do the permutations, 12 NPR3. We get one of these two options. Now, in this case, really, order is going to matter. So the idea is that if you swap the president and vice president around, we're going to think of that being sort of a different selection. So really, this time, I'm going to do the 12 NPR3. 12 math prob NPR3. And that just gives me, whoops, 1320. Again, you really want to write down 12 NPR3. Just to show your work here, and that way you get partial credit if, like, you go to your calculator and you mistype in 12 NPR3 or something. Okay, so that's going to end here this solution.